Hello, everyone. Welcome to my talk. I'm Yizhou from Southern University of Science and Technology. I would like to thank the organizer for giving me the opportunity to talk about parity violation in scalar-induced gravitational waves. We consider ghost inflation as an example to realize this parity violation. This talk is based on the work with Sebastian and Zhiming. Let's start with some background and motivation. First, much information about the early universe is obtained from CMB observations, but CMB is almost blind about the modes re-enter the horizon long before last scattering surface. So, a perfect complement to CMB would be gravitational wave observations, because gravitational wave, once be product, they hardly interact with matter. So they may still carry the information about the early universe. On the other hand, is CMB constraint is mainly on large scales. The small scale scalar perturbation could be very large. Then it could be responsible for the production of primordial black holes and scalar-induced gravitational waves. The primordial black holes are considered as a constituent of dark matter, while scalar-induced gravitational waves can be detected by gravitational wave observations. Recently, some papers pointed out that scalar-induced gravitational waves can explain the PTA data, so we may already detected scalar-induced gravitational waves. Then what are scalar-induced gravitational waves? They are just tensor perturbations sourced by first-order scalar perturbations. For example, this is a metric perturbation in Newtonian gauge where phi and h are scalar and tensor perturbations, respectively. At a linear order, they evolve independently, but they are mixed in higher orders. This is the equation for the second-order tensor perturbation. The quadratic terms on the right-hand side of the first-order scalar perturbations play the role of gravitational wave source, so we have the name scalar-induced gravitational waves. Then we solve this equation, and because the small-scale modes re-enter the horizon before last scattering surface, so we take the background as in radiation era. Then the power spectrum for tensor perturbation can be written into this form, where the function I contains the information about the post-inflationary evolution of the scalar source, and thus the 4-point function of zeta is valued at the end of inflation. The 4-point function of zeta can be further divided into disconnected part and connected part. The disconnected part contains two 2-point functions, while the connected part contains contact and exchange diagrams. At the tray level, the disconnected part corresponds to Gaussian contribution, while the connected part is non-Gaussianity. Explicitly, the disconnected 4-point function is proportional to 2-power spectrum, and the connected part is called the trispectrum. The very important point here is that trispectrum is the lowest order scalar correlation function that can be parity violation, as was studied in these papers. Now comes the question: if the trispectrum is parity-odd, what about the gravitational waves they induce? Well, we expect that the scalar-induced gravitational wave will also be parity-violating, in the sense that the right-handed polarized gravitational waves differs from the left-handed one. In fact, in gravity theory that breaks parity symmetry, scalar-induced gravitational waves do have parity violation. For example, as proposed in this paper, In Chern-Simons gravity coupled with a dynamic scalar field, the equation of motion for tensor perturbation are different for different polarizations. So both gravitational wave spectrum and the chirality, which is defined as the difference between chiral polarizations over the total power spectrum. These two are both modified by Chern-Simons term, and the non-zero chirality indicates the existence of parity-violating. But here, in this talk, I will consider the gravity theory is just Einstein's general relativity. The parity violation is totally from the scalar trispectrum. To say if the scalar-induced gravitation wave can be parity violating in general relativity, we take a look at the polarizations. This polarization tensor for chiral basis. We observe that the only difference between different polarizations is the azimuthal angle dependence from the factor Q here. This is the expressions. So if scalar-induced gravitation wave can be parity violating, then there must be something to do with azimuthal angles. So to see this, we recast the power spectrum into this form, where we manifest the azimuthal angle integrals and put all other things into the function f. The dependence of function f on azimuthal angles is totally from the Fourier function of theta. And because of the rotational invariance, the function f must be a function of the difference between azimuthal angles. And for the same reason, f must be periodic about psi with a period 2 pi. Let's first look at the disconnected part. The dependence on azimuthal angles for disconnected part is totally from the delta functions. And we notice that the two terms are symmetric inside the integral over Q2. So we can isolate the delta psi out and write the function f into this form. Then we perform the integral explicitly to get this result. This result shows that all polarizations contribute equally for disconnected part. Therefore, there's no PV effect. Now we turn to the connected part. We take a change of variables and perform the chi-integrals explicitly to get these expressions, from which we see that first, the linear polarized scalar-induced gravitation waves always contribute equally. This actually is simply from the rotational invariance, because plus and cos are related by a rotation. Second, since the function f is periodic, we Fourier expand it into this form. The total power spectrum pH is non-zero only if the coefficient C2 is non-zero. On the other hand, the difference between chiral polarizations is non-zero only if the coefficient S2 is non-zero. So it is possible that the connected scalar-induced gravitation waves can be parity-violating. But so far, these conclusions are rather abstract. So to be more concrete, we recall all the scalars that can be built out of the three momentum here. The first five are independent of azimuthal angles. Only the blue two are relevant. The dot product is proportional to the cosine psi, while the another one is proportional to sine psi. I will call it the mixed product. Therefore, the function f can be regarded as a function of cosine psi and sine psi. So we have two expressions for the total power spectrum. From these two expressions, we see that first, the scalar trispectrum must not be odd function of mixed product for the total power spectrum to be non-zero. But we know that a parity-odd scalar trispectrum is exactly an odd function of mixed product, so a parity-odd trispectrum has no contribution to the total amount of scalar-induced gravitation wave. So it seems the parity-odd trispectrum have no effect on scalar-induced gravitation waves because they do not induce anything. But this is not the case. I will explain this too. On the other hand, if the trispectrum is even in mixed product, then it cannot be odd in dot product for the total power spectrum to be non-zero. To sum up, the trispectrum must be even in both mixed product and dot product to get a non-zero total power spectrum. This is a necessary condition, not sufficient. Let's look at the chirality. The difference between chiral polarizations is given by this expression. First, we notice that first, the trispectrum must not be even in psi to break the parity. It must be an odd function of mixed product. Second, if the trispectrum is odd in mixed product, it cannot be even in dot product to break the parity. For example, this trispectrum changes sign under parity transformation, but will not induce parity violation. So we conclude that to break parity symmetry, the scalar trispectrum must be of this form, which is a necessary and sufficient condition if we assume polynomial dependence. The sufficient part can be proved by this formula. Now we have a problem because the chirality is defined as the difference over the total power spectrum. But for a parity-odd trispectrum, the total power spectrum is 0, so this quantity is not well defined. To see this problem, we take a look at these two equations. They imply that at least one of the two is negative. So the question becomes how to understand a negative power spectrum. We emphasize that the connected part should be regarded as a correction to the disconnected part. So a negative power spectrum means a separation with respect to the disconnected part. And a positive one means an enhancement. So a zero connected total power spectrum does not mean that it has no effect. It just won't change the total amount of disconnected power spectrum. In this sense, the chirality should be understood as be given by this formula, which is not well defined. Then the next question is how large is the PV effect? Well, as proposed in this paper, the connected scalar-induced gravitation wave is bounded by the requirement of perturbative control. So the ratio as well as the chirality is proportional to the one-loop power spectrum over a tree-level power spectrum, which should be much smaller than unity. However, we notice that there are 2 points that may relax the bound. First, this estimation overlooked very complicated integrals, which is not clear to be of order 1. Second, there is factor 1 over 4 pi squared in the loops that could relax the bound for 2 orders. So it would be good to have a specific inflation model to realize this parity violation to estimate how large the PV factor will be. But according to the non-Gaussian theorem proposed by these papers, it is not easy to realize parity-odd trispectrum of massless scalar from Bunch-Davis vacuum without breaking scale invariance. So we consider ghost inflation, which preserves scale invariance and can break parity symmetry. Ghost inflation has a nonlinear dispersion relation. It originates from non-Bunch-Davis vacuum and thus bypasses non-Gaussian theorem. So the free field action for the Gaussian field is given by this equation. We will consider two parity-even interactions and two parity-odd interactions as given by these papers. The trispectral for the for these diagrams are very complicated. I just write them here schematically, and we see that the parity-even trispectral are in even powers of mixed product, so they induce total power spectrum, but will not induce parity-violation. In contrary, the parity-odd trispectral are in odd power of mixed product and dot product, so they induce parity-violation, but not the total power spectrum. We numerically computed the connected scalar-induced gravitational wave as well as the chiralities. We find that the ratios and the chiralities are all much less than 10%, so they are highly restricted. In summary, we showed that even in general relativity, the trispectrum-induced gravitational waves can be parity-violating, provided the scalar trispectrum has the following form. Second, the parity-odd scalar trispectrum will not change the total amount of scalar-induced gravitational waves. Next, requiring perturbative control, the connected scalar-induced gravitational wave and the difference between chiral polarizations are constrained to be relatively small compared to the disconnected part. In Gaussian inflation, the connected scalar-induced gravitational wave and the difference are smaller than 10% of the disconnected part. So finally, I would like to emphasize that the parity-even connected scalar-induced gravitational wave is degenerate with the disconnected part. So it is hard to distinguish them, but the parity-violation signal is non-degenerate with the parity-even part. So it will be easier to find the parity-violation signal than to find the parity-even signal from the connected part. So that's my talk. Thanks for listening.